The date was October 21st, 25. It was a Tuesday. If you looked at the world from a sidewalk cafe in Paris or through the window of a high-rise apartment in Tokyo, the day felt completely ordinary. In New York, the morning traffic was just as heavy as it always was. People were honking their horns, spilling their coffee, and worrying about being late for meetings that could have been emails. The sun came up, casting its usual light over the skyscrapers and the parks. It was the kind of light that promised a routine day, the kind of day where the biggest problem a person might face was a dead phone battery or a forgotten umbrella. We often think that history changes with a loud bang. We imagine explosions, sirens, and people running in the streets. We expect the sky to turn red or the ground to shake when the world changes forever. But on this specific Tuesday, the change did not come with a bang. It arrived with a silence so deep and profound that no one outside of a small windowless room in California even knew it had happened. This is the fragility of our public understanding. We live our lives on a thin sheet of ice, believing it is solid ground. We laugh, we cry, we plan for vacations next summer, completely unaware of the dark, cold water moving beneath us. We assume that if something truly massive were happening, we would know. We assume the news would tell us. We are wrong. At the Jet Propulsion Laboratory in Pasadena, the air conditioning was humming with a low, steady drone. It was 3 a.m. local time. The room smelled of stale donuts and the sharp metallic scent of overheated electronics. Inside this room, a man named Elias was staring at a monitor. He was not a hero. He was just a data analyst with a bad back and a mortgage he was struggling to pay. His job was to look at lines of code that represented background noise from deep space. Most of the time, space is noisy. It is filled with the static of dying stars, the radiation left over from the Big Bang, and the random chatter of the universe. To the human ear, it sounds like static on an old radio. To Elias, it usually looked like a messy, jagged line on his screen. But at exactly 3:14 in the morning, the jagged line stopped. It did not flatline, it organized itself. Elias blinked, rubbing his eyes. He reached for his cold coffee, assuming he was hallucinating from lack of sleep. He looked back at the screen. The data was still there. It was coming from the direction of the Kepler sector, a patch of sky that was supposed to be quiet. The data was not random. In nature, numbers are messy. Nature deals in fractions and chaos. But this signal was perfect. It was a series of pulses. 1, then a pause. 2, then a pause. 3, then a pause. It repeated. Then the signal changed. It began to display a frequency that Elias recognized immediately, not as a random cosmic event, but as a mathematical constant. It was the frequency of hydrogen multiplied exactly by pi. Elias sat frozen. His heart began to hammer against his ribs at a frantic rhythm that felt too loud in the silent room. He typed a command into his keyboard to check the sensors. Maybe the satellite was broken. Maybe it was a glitch in the software. "Come on," he whispered to himself. "Be a glitch. Please be a glitch." The system ran a diagnostic. The result came back in green text sensors optimal. Signal confirmed. He looked at the raw numbers. The signal strength was impossible. For a signal to be this clear from that distance, the energy source had to be greater than our entire sun, and yet it was focused. It was not a broadcast meant for the whole universe. It was a beam, a tight, narrow beam pointed directly at Earth. Elias reached for the red phone on his desk. This was the protocol. If you see something that cannot be explained by physics, you call the supervisor. But before his hand could touch the receiver, his monitor changed. The screen flickered once. The data vanished. In its place, a single message appeared in a plain grey box. It did not ask for a password. It did not ask for confirmation. It simply read, "Protocol 9 initiated, coordinated silence active." Elias pulled his hand back as if the phone were hot. He knew what Protocol 99 was, though he had only ever read about it in the theoretical appendices of his employment handbook. It was the highest level of containment. It meant that the system had automatically detected an artificial intelligence or an artificial signal of non-human origin. But the most terrifying part was the phrase coordinated silence. It meant that Elias wasn't the only one seeing this. It meant that across the world, at the European Space Agency, at the observatories in Chile, and at the tracking stations in Australia, other screens were going black. It meant that the internet filters were already rising. It meant that if he tried to email this data to his wife, the email would never leave his outbox. If he tried to post it on social media, the post would instantly vanish. The machine had reacted faster than he could. The government, or whoever had built this algorithm, had decided that the world was not ready to know. Elias stood up and walked to the window. He pulled back the blinds. Outside, the parking lot was empty. The streetlights hummed with an orange glow. In the distance, he could see the headlights of a single car driving down the highway. That driver was probably listening to music, thinking about breakfast, or worrying about a job interview. That driver had no idea that the sky had just changed. That driver had no idea that the universe was no longer a lonely place. Elias felt a wave of nausea. He looked at his hands, they were shaking. The distance between him and the rest of humanity had suddenly become infinite. He was holding a secret that could shatter. Religion topple governments and rewrite history. And yet outside the world kept turning. The coffee in his mug was still rippling slightly from when he had set it down. It was a terrifying realization. The most important event in human history had just occurred, and the immediate reaction of the powers that be was not to celebrate, not to panic, but to silence it. They wrapped the truth in a blanket of darkness before it could even take its first breath. The monitor behind him made a soft beep. The grey box disappeared. The screen returned to the jagged, messy line of random static. The perfect signal was gone, deleted from the local record, buried deep in a server that only a handful of people could access. It was as if it never happened. But Elias knew. The silence in the room felt heavier now. It wasn't just the absence of noise, it was the presence of a secret. He sat back down in his chair. He looked at the fake static on the screen. He realized then that the normalcy of the world was a lie. It was a curated experience a show kept running to keep people calm, to keep them working, to keep them buying coffee and paying taxes. The real world, the world where something was calling out to us from the dark, was hidden behind a wall of coordinated pun. Elias took a sip of his cold coffee. It tasted bitter. He looked at the clock. It was 3:20 in the morning. The sun would rise in a few hours. People would wake up. They would brush their teeth. They would kiss their children goodbye. They would complain about the weather. And all the while, the whisper would be there, buried in the data waiting. The signal had not ended. Elias knew this with a certainty that made his stomach turn. The signal had not stopped. We had just stopped listening. In the vast, silent theatre of the cosmos, there are moments when the main stage is hidden from the audience not by darkness, but by an overwhelming excess of light. This phenomenon is what astronomers call solar conjunction. To understand this, imagine you are trying to spot a small firefly hovering directly behind a massive stadium spotlight that is pointed straight at your face. The firefly is there alive and glowing, but the sheer intensity of the spotlight completely erases it from your vision. In the context of our solar system, a solar conjunction occurs when a planet or another celestial body moves to the opposite side of the Sun relative to Earth. The three objects, Earth, the Sun, and the target object, form a nearly straight line. For the comet 3I Atlas, this alignment is not just a geometrical curiosity, it is a total blackout. The comet has drifted into the one place in the solar system where our eyes cannot follow it, the region directly behind the Sun. This positioning creates a frustrating paradox for scientists. We possess the most advanced technology in human history. We have built telescopes that can peer back to the dawn of time and detect the heat signature of galaxies billions of light years away. Yet right now we are effectively blind to an object right in our own backyard. The Sun, usually our source of illumination, has become an impenetrable curtain. The position of 3I Atlas behind the Sun is critical because of when it is happening. Comets are most active, most volatile, and most scientifically interesting when they are closest to the star. This point, known as perihelion, is when the ice on the comet sublimates violently, turning directly into gas. It is when the tail grows longest and the internal structure of the comet is put to the ultimate test. It is the climax of the comet's journey. And precisely at this climax, the curtain falls. We are forced to miss the most dramatic scenes of the play because the stage lights are too bright. This situation highlights the ironic fragility of our observation methods. Our space telescopes like the Hubble or the James Webb are incredibly sensitive instruments designed to catch the faintest glimmers of light from the deep dark. Because they are so sensitive, they have a major weakness: they cannot look anywhere near the Sun. Pointing a sensitive optical telescope at the Sun would be like looking at the Sun with binoculars. It would fry the sensors instantly. Therefore, as 3I Atlas moves closer to the solar disk, we must deliberately turn our expensive machines away to protect them. We have to look away exactly when we want to look most closely. There is a profound and somewhat terrifying beauty in this brilliant blind spot. It forces us to confront the true nature of the Sun. On a normal day, we think of the Sun as a benevolent yellow circle in the sky that gives us warmth and defines our days. But in moments like a solar conjunction, the Sun reveals its true identity, a raging, chaotic monster of nuclear fusion. It is a billion times louder, brighter, and more powerful than anything else around it. It screams across the entire electromagnetic spectrum, drowning out all other whispers in the void. This leads to a humbling contemplation on the limits of human power. We often pride ourselves on conquering nature. We have mapped the continents, split the atom, and sent probes to the edge of interstellar space. But here simple geometry and raw brightness defeat us. We are reminded that we are small creatures living in the orbit of a massive star. When the sun decides to hide something, it stays hidden. No amount of coding, no algorithm, and no amount of money can make the sun transparent. We are at the mercy of celestial mechanics. The blindness we experience here is different from the darkness of the night. Usually we fear the dark because we cannot see what is lurking within it. But this is a blindness caused by glory. It is a white out. It is a reminder that too much truth, too much power, and too much light can be just as obscuring as a shadow. The comet is bathed in more light now than it has ever been in its existence, yet to us it's invisible. For the astronomers and the global community watching 3i Atlas, this period is defined by an agonizing sense of waiting. It is a suspense thriller where the screen has gone blank. While the comet is behind the sun, it is being battered by solar winds and intense radiation. Is the nucleus holding together? Is the heat causing the comet to break apart into a cloud of dust and gravel? Or is it surviving the fire to emerge on the other side as a spectacular object in our night sky? We simply do not know. We are stuck in a radio silence, unable to see, unable to communicate, and unable to measure. We are reduced to the ancient human act of waiting. We must wait for the geometry to shift, for the Earth to move further along its orbit, and for the comet to peek out from behind the solar glare. There is a quiet tension in this waiting. It is the feeling of holding your breath underwater. We know that a dramatic struggle for survival is happening right now, millions of kilometers away, hidden within the glare. The comet is fighting for its life against the gravity and heat of the sun. When it finally re-emerges from this brilliant blind spot, we will not just see a comet, we will see a survivor or the wreckage of a fallen traveller. Until then, we can only stare at the blank bright space in our data, and respect the overwhelming power of the star that sustains us yet blocks our view. It teaches us patience. It teaches us that despite our satellites and our supercomputers, there are still places we cannot look and secrets we cannot steal until the universe is ready to reveal them. The blind spot is a check on our arrogance, a dazzling reminder that we are still just watchers on the shore squinting into the light. The hypothesis presented by Stefan Burns offers a fascinating and somewhat terrifying perspective on how our solar system operates. It suggests that the sun is not just an isolated ball of fire burning alone in the center of the solar system, but rather a highly sensitive electrical engine that interacts with everything around it. In this third part, we explore the specific prediction regarding the events of October 20th and the dramatic interaction between two opposing forces, the blazing heat of the sun and the frozen heart of a comet. The prediction of the October 20th event. Stefan Burns, a researcher who closely studies the electrical patterns of the weather and the sun, identified a critical window of time around October 20th. His theory relies on the idea of cosmic alignment and electrical connection. Just as the moon affects the tides of the ocean on Earth, Burns suggests that celestial bodies moving through space can affect the tides of plasma on the sun. For this specific date, the focus is on a sun grazer, a comet or a large icy body that dives dangerously close to the sun. In the standard model of astronomy, we often think of a comet simply getting hot and melting as it gets near a star. However, Burns proposes a much more energetic reaction. He argues that when a comet enters the sun's outer atmosphere known as the corona, it does not just melt, it triggers a violent electrical reaction. The prediction for October 20th was based on the calculation of this icy body's path. The theory posits that as this object screams through space toward the sun, it acts like a trigger. The sun is currently in a state of high activity known as the solar maximum. Its magnetic fields are tangled and tense like rubber bands stretched to their breaking point. The arrival of the ice, the comet, provides the spark that snaps these bands. The result is a prediction of a massive coronal mass ejection or CME exploding outward from the sun on or around this date. The interaction of fire and ice. To understand why a piece of ice can disturb a giant ball of fire, we have to look at the electrical nature of the universe. This is the core of the fire and ice concept. The sun is the fire. It is a massive sphere of plasma. Plasma is the fourth state of matter where gas becomes so hot that the electrons are ripped away from their atoms. This means the sun is electrically charged and creates a gigantic magnetic field that stretches far past the planets. The comet is the ice. It comes from the cold, dark outer edges of the solar system. It carries a different electrical charge than the sun. In simple terms, you can imagine the sun as the positive end of a giant battery and the comet as a small negative wire. As long as the comet is far away, nothing happens. But as it dives toward the Sun on October the 20th, it moves rapidly through the Sun's magnetic environment. In physics, when you move a conductor, the comet through a magnetic field, the Sun, you generate an electrical current. Burns hypothesizes that the size of the comet doesn't matter as much as the speed and the charge difference. As the icy body penetrates the hot corona, the difference in voltage between the two objects becomes too great to sustain. The vacuum of space acts as an insulator, keeping them apart, but eventually the gap becomes too small. The result is a cosmic short circuit. The ice rapidly turns to gas, creating a bridge for electricity to flow. This sudden discharge destabilizes the magnetic fields of the Sun in that specific region. The energy stored in those magnetic fields has to go somewhere. It erupts outward. This is the coronal mass ejection. 1 billion tons of hot plasma and magnetic force blasted into space at millions of miles per hour. Contemplation, the dance of invisible giants. When we close our eyes and try to visualize this event, we must look beyond what human eyes can see. We must try to see the universe through the lens of energy and magnetism. Imagine the Sun not as a yellow circle, but as a living, breathing ocean of electric fire. Its surface is not solid, it is a shifting landscape of arcs and loops. These are magnetic field lines. They look like invisible fountains shooting up from the surface, twisting and diving back down. They form a complex, invisible cage around the star. These lines are under immense tension, holding back the fury of the nuclear reactions inside. Now picture the intruder. The comet is a cold, silent traveller. It has spent thousands of years in the absolute zero of deep space. It is a ghost made of dirty ice and rock. As it approaches the Sun, it is invisible to the naked eye against the blinding glare of the star. But in the realm of electromagnetism, the comet is screaming. As it cuts through the invisible magnetic webs of the Sun, it creates a wake just like a boat moving through water. But this wake is made of electrical disturbance. The moment of interaction is a collision of opposites. It is the ultimate meeting of fire and ice. It is not a physical crash like two cars hitting each other. It is a touch of energies. Visualize the magnetic field lines of the Sun as the strings of a giant guitar. They are pulled tight. The comet is the finger that plucks the string. When the comet passes through, it snaps the magnetic line. This phenomenon is called magnetic reconnection. In that split second, the invisible tension breaks. The magnetic lines snap and reconnect into a new shape. This snapping motion releases a catastrophic amount of energy. It is a silent explosion in the vacuum of space, yet it is powerful enough to strip the atmosphere off a planet if it were too close. The ice may be vaporized instantly, turning from a solid rock into a cloud of charged gas in a fraction of a second, but in its death it provokes the fire. The Sun recoils, a massive bubble of plasma lifts off the surface, riding the shockwave of the magnetic snap. This is the beauty and the terror of the electric universe. We live our lives on Earth feeling the gentle warmth of the Sun on our skin, completely unaware of the violent, silent war happening above us. We do not see the magnetic spiderwebs that fill the solar system. We do not feel the tension building up in the empty space between the planets. The hypothesis of Stephen Burns reminds us that space is not empty. It is alive with invisible rivers of current and fields of force. The event of October 20th serves as a reminder that even a small cold object can shake a giant if it touches the right nerve. It is a dance of physics where the smallest spark can ignite the greatest fire, and where the invisible forces of nature dictate the fate of worlds. It begins not with a bang, but with a flicker on a screen in the middle of the night. The story of the whistleblower is almost an urban legend, now passed around in private chat rooms and archived on hard drives that are kept offline. It happened on a Tuesday during the quiet hours when the traffic on the Western Hemisphere slows down. A user claiming to be a data analyst from a prominent observatory uploaded a single thread to a public science forum. There was no sensational title, no use of capital letters to grab attention. It was just a raw data dump. The user claimed that for 12 seconds their sensors had picked up a spike in high-energy gamma radiation. In the world of astronomy, gamma rays are the most energetic form of light. They usually come from the most violent events in the universe, like exploding stars or black holes colliding. But natural gamma ray bursts are chaotic and messy. They look like a splash of paint on a canvas. The image this user posted was different. It showed a signal that was rhythmic. It pulsed. Up, down, up, down. It looked like a heartbeat or perhaps a machine breathing. The energy levels described were massive, written out as billions of electron volts, numbers so high they are difficult to comprehend. The coordinates pointed to a patch of empty space where nothing should be. For about 40 minutes, the post sat there. A few night shift students and amateur astronomers commented on it. They asked for verification. They asked if it was a calibration error or a glitch in the telescope. The original poster replied only once. The calibration is perfect. The background noise is 0. This is not a mistake. And then the ghosting began. If you tried to refresh the page, you received a 404 error. The thread was gone. This happens on the internet all the time. Moderators delete off-topic posts or users get cold feet and remove their own words. But this was different. The user's account didn't just show as deleted, it was as if it had never existed. The cached versions of the page, the automatic snapshots taken by search engines, were wiped clean within the hour. Usually when something is deleted from the internet, it leaves a scar. Broken links remain, screenshots float around on social media. But in this case, the digital scrubbing was surgical, it was efficient, it was terrifyingly fast. The only reason we know about it is because 3 people managed to save the image of the graph to their local desktops before the connection was severed. This brings us to the unsettling concept of ghost in the data. We tend to view the internet as a permanent library, a place where everything is remembered forever. We assume that once something is online, it is immortal. But the truth is far more fragile. Information is fluid. It can be altered, suppressed, or erased by those who hold the keys to the servers. When that data vanished, the signal transformed from a scientific curiosity into a ghost. It haunts us not because of what it showed, but because of its absence. Why did it disappear? That is the question that keeps the curious awake at night. There are 2 possibilities, and both are disturbing in their own way. The first possibility is that it was a hoax, a fake created by someone wanting to cause trouble, and the moderators removed it to prevent panic. This is the rational explanation. It is the safe explanation. The second possibility is that it was true. This leads us to a deep contemplation on the nature of truth and rumour in the digital age. When official channels go silent, rumours rush in to fill the vacuum. The silence itself becomes a piece of data. If the signal was just a glitch, why scrub the user from existence? Why not just tag the post as error? The aggressive removal suggests fear. And if the authorities are afraid, then we start to wonder if we should be afraid too. We humans have a primal fear of anomalies. We build our lives around patterns and predictability. The sun rises, the sun sets. The seasons change. We understand the laws of physics. When something comes along that breaks those rules like a rhythmic signal from empty space, it triggers a deep instinctual alarm. It suggests that our model of reality is incomplete. It suggests that we are small and vulnerable in a vast dark room and something else is in there with us. However, we must be careful. There is a fine line between being observant and being paranoid. The internet is full of noise. For every one genuine whistleblower, there are 1,000 people making things up for attention. If we believe every shadow is a monster, we lose our grip on reality. We cannot let our imagination run wild every time a server crashes or a file goes missing. Yet history has taught us that healthy skepticism is necessary. We remember the times when conspiracy theories turned out to be facts. We remember when governments denied the existence of certain surveillance programs only for the truth to come out years later. We remember times when industrial accidents were covered up to protect stock prices, while people living nearby fell ill. These historical scars make us suspicious. They make us look at the empty space where the data used to be and wonder what is being hidden. The ghost of the gamma ray signal serves as a reminder. It reminds us that truth is not always what is presented to us on the surface. Sometimes the truth is found in the gaps in the things that are removed and in the silence that follows a loud noise. Whether the signal was a message from another civilization, a secret military test, or simply a bored student with Photoshop, the result is the same. It forced us to look at the darkness and question what we know, reminded us that while data can be deleted, the memory of it cannot be easily erased. We are the keepers of these ghosts. We hold on to the screenshots and the stories not because we are certain they are true, but because we are terrified of a world where we are not allowed to ask if they are. In the end, the most haunting part is not the signal itself. It is the realization that we rely on systems of information that we do not control. We are staring at screens, waiting for a flicker, hoping that next time we will be quick enough to catch the ghost before it fades away into the black static of the forgotten. To the naked eye, the night sky is a static tapestry of white dots, a beautiful but silent display. However, to an astronomer armed with the right instruments, that light is not silent at all. It is a loud, chaotic, and incredibly detailed conversation. Every beam of light that travels across the cosmos carries a hidden backpack of information, a cargo of data that tells us exactly what the sender is made of. When we looked at the visitor passing through our neighbourhood, we didn't just take a picture of its shape, we tried to read its DNA. This process is the bedrock of modern astrophysics, a technique known as spectroscopy. If you have ever seen light pass through a glass prism and shatter into a rainbow on the wall, you have seen the basic engine of spectroscopy. Light from a star or sunlight reflecting off an asteroid appears white or yellowish to us, but that white light is actually a bundle of every colour in the visible spectrum tightly packed together. When scientists catch that light in a telescope and run it through a spectrograph, a highly advanced version of that glass prism, they spread the light out into a long coloured ribbon. If the object were a perfect glowing solid, that ribbon would be a smooth, continuous fade from violet to red. But celestial objects are rarely perfect solids. They are surrounded by gases, atmospheres, or dust. This is where the magic happens. As the light pushes through the atoms on the surface of an object like Oumuamua or the coma of an interstellar comet, those atoms get hungry. Every chemical element in the universe, hydrogen, helium, carbon, iron, has a unique appetite. They only absorb light at very specific energy levels which correspond to very specific colours. Imagine walking down a buffet line where one person only eats the green beans and another only takes the mashed potatoes. When you look at the trays at the end of the line, the empty spots tell you exactly who ate there. In the cosmic spectrum, these empty spots appear as dark black lines cutting vertically across the rainbow. These are called absorption lines. They are the fingerprints of the stars. By measuring exactly where these black lines fall on the colour spectrum, scientists can list the ingredients of an object that is millions of miles away without ever touching it. This brings us to the hunt for the anomaly specifically regarding heavy metals like nickel and iron. In our own solar system, we have a very good understanding of the family recipe. The Sun and the planets formed from the same cloud of gas and dust known as the solar nebula. Because everything was cooked in the same kitchen, the ratio of elements is fairly consistent. We know roughly how much nickel usually appears alongside iron in comets and asteroids that belong to our system. It is a predictable standard, a baseline that has been established over decades of observation. When astronomers analyse the light reflecting off an interloper, or the faint gas released if it begins to heat up, they are looking for a match to this baseline. They measure the strength of the iron lines and compare them to the nickel lines. This is where the thrill of the unknown kicks in. If the visitor truly comes from deep space, it likely formed around a different star in a different nebula, with a completely different chemical history. Perhaps its parent star was richer in heavy metals, or perhaps the object formed in a region where the temperature froze out different elements than what we see here. A significantly weird ratio of nickel to iron is like finding a book written in a different grammatical structure. It is immediate, undeniable proof that this object is not from around here. Reading this chemical composition is an exercise in extreme precision. The light from these objects is often incredibly faint, especially as they speed away from us. Astronomers have to capture photons, individual particles of light, one by one, accumulating them over hours to build a spectrum bright enough to read. It is like trying to reconstruct a song by listening to a faint whisper from 3 rooms away. But when the graph finally forms and the dark lines appear, the chemicals confess their presence. Here is the iron, the spectrum says. Here is the water ice. Here is the organic carbon. The contemplation. There is a profound, almost spiritual weight to this scientific process. It forces us to stop and consider the nature of the messenger itself, the light. Consider the journey of the photons that hit the detector. These particles of light may have travelled for millions of years, or perhaps just minutes, from the sun to the object and then back to us. They have crossed the freezing absolute vacuum of the void. They have carried the signature of that lonely rock through the silence of space, preserving the information perfectly until they smashed into the mirrors of our telescopes. It is staggering to realise that we can touch the physical reality of a distant world just by catching its reflection. We do not need to send a spaceship to drill a core sample. The universe is constantly broadcasting its composition to anyone clever enough to build a receiver. But the emotional impact hits hardest when the data reveals something wrong. When the nickel to iron ratio doesn't fit, or the nitrogen abundance is off the charts, or the surface redness doesn't match the asteroids in the belt, a distinct feeling washes over the observer. It is a mix of excitement and a strange primal unease. For centuries, humans have mapped the solar system. We know the planets like our own siblings. We know the asteroids like cousins. We recognise the family resemblance in their chemical makeup. Finding an object with a fingerprint that doesn't match is like sitting at your family dinner table looking at a person who resembles your brother, but realising their eyes are a colour you have never seen in your family line. It is a realisation of foreignness. It reminds us that our solar system is just a tiny enclosed bubble, a local island with its own specific rules and ingredients. Beyond the edge of our sun's influence lies a galaxy that is vast, varied and chaotic. There are other kitchens cooking with different recipes. Holding that piece of data, that single graph showing a chemical ratio that shouldn't exist, is like holding a postcard from a stranger. It is proof that the dark emptiness between the stars is not empty at all, but full of wanderers carrying the history of dead suns and alien worlds. It changes the way we look up. We are no longer just looking at lights in the sky. We are looking at an ocean of potential waiting for the next bottle to wash up on our shores. When we look up at the night sky, we usually expect a certain level of politeness from the universe. We expect planets to march in neat circles, stars to shine with a steady hand, and comets to follow the instructions written by gravity. We call this the music of the spheres, a grand, orderly orchestra where every instrument plays on time. But there is a secret library within astronomy, a collection of events that refuse to follow the script. We can call this the catalogue of impossibilities. These are the rebels of the cosmos. They are the objects that zig when they should zag, the lights that fade when they should flare, and the structures that look physically impossible to the human eye. The dance of the strange orbits. The first entry in our catalogue concerns movement. In a simple solar system, everything should move somewhat like a car on a racetrack. The track is flat and everyone drives in the same direction. However, deep space observers have found travellers that ignore this rule entirely. We have observed objects with hyperbolic trajectories. In simple terms, these are objects moving so fast that the sun cannot catch them. They are not here to stay. They are merely passing through. They do not draw a closed circle or an oval. They draw a completely open curve. They enter our neighbourhood at incredible speeds, tens of thousands of kilometres per hour faster than anything native to our system, and then shoot back out into the void, never to return. Even stranger are the objects that suffer from non-gravitational acceleration. Usually the only thing that changes an object's speed in space is gravity. But we have seen visitors like the famous interstellar scout Oumuamua that seem to push themselves. As it left the solar system, it sped up slightly more than gravity could explain. It was as if it had a hidden engine. The likely explanation is outgassing jets of invisible gas pushing the rock like a thruster, but because we could not see the gas, it remains a beautiful anomaly in our data. Then there are the objects with extreme inclinations. Imagine a dinner plate representing the solar system. Most planets roll around on the plate, but some of these strange objects dive-bomb the plate from above, piercing through it at a 90-degree angle. These vertical orbits suggest a chaotic past, perhaps a violent kick from a giant planet billions of years ago that threw them into this lonely perpendicular path. The anti-tail phenomenon. Perhaps nothing is as visually confusing as the anti-tail. When we draw a comet in a child's notebook, we always draw the tail streaming behind it, flowing away from the sun like hair blowing in the wind. This makes sense because the solar wind pushes the dust away. However, astronomers sometimes see a comet with a spike pointing in the exact opposite direction, pointing directly at the sun. This looks like a physical impossibility. How can dust flow against the solar wind? This is not a violation of physics, but a grand illusion of perspective. It is a trick of geometry. When the Earth crosses the plane of the comet's orbit, we see the spread of heavy dust particles left behind by the comet. Because of our specific viewing angle, this wide fan of dust appears to overlap with the front of the comet. It looks like a spear tip projecting forward, but it is actually a trail of old dust seen edge on. It reminds us that what we see depends entirely on where we stand. Even in space, point of view is everything. The light that breaks the rules. The third chapter of our catalogue deals with brightness. There is a standard rule called the inverse square law. Simply put, as a comet or asteroid gets closer to the sun, it should get brighter in a predictable way. If it cuts the distance in half, it should get significantly brighter. But the catalogue of impossibilities is full of light curves that look like roller coasters. We see comets that are approaching the sun but suddenly go dim, known as a fizzling event. This often happens because the comet runs out of ice on its surface, essentially turning off its own light switch just when the show should be starting. Conversely, we see outbursts. A distinct object millions of kilometers away will suddenly brighten by a factor of 1,000 in a single hour. This is violent and explosive, and it usually means a pocket of gas trapped deep under the ice has finally burst, blasting the surface apart and creating a massive cloud of reflective dust instantly. These events are unpredictable. They turn a faint smudge in the telescope into a naked eye wonder for a few days only to vanish again. These fluctuations tell us that these bodies are not solid rocks, but dynamic, shifting and fragile worlds that evolve in real time. The beauty of chaos. Why do we obsess over these anomalies? There is a profound beauty in this chaos. If the universe were perfectly orderly, it would be a machine. Machines are useful, but they are not alive. The anomalies, the wobbling orbits, the backwards tails, the flickering lights suggest that the universe is a dynamic, evolving environment. Chaos is not a mistake. Chaos is complexity. The fact that a rock can tumble through space, heat up, crack, open, and jet away on a cushion of gas shows a richness of interaction. It shows that matter is constantly struggling against energy. The smooth clockwork of the solar system is just an average. The reality is a messy, colliding, exploding, beautiful storm. Why exceptions matter more than rules? In science, we are often taught to look for the pattern. We want the equation that fits 99% of the data. But the history of discovery teaches us that the 1%, the exception, is where the revolution hides. If we only study the planets that orbit perfectly, we only confirm what we already know. It is the glitch that teaches us something new. When astronomers noticed that the planet Uranus was moving slightly wrong, they didn't ignore it. They focused on the error. That error led them to calculate the existence of Neptune. The anomalies in our catalogue are the keys to the next door of knowledge. A comet that brightens too fast might reveal a new type of chemical ice. An orbit that is too fast might reveal the presence of dark matter or a hidden planet. The rule confirms the past, but the exception builds the future. We should not fear the data that ruins our theories. We should celebrate it. The humility of science. Ultimately, the catalogue of impossibilities teaches us humility. We humans like to believe we have mapped the solar system. We have named the planets, calculated their weights and measured their years. We feel like masters of our domain. But then a rock from another star zooms past us at a speed we cannot catch. Or a comet creates a tail that looks like it defies gravity. Or a star dips in brightness in a way that no model can explain. These moments stop us in our tracks. They remind us that we are standing on the shore of a vast dark ocean holding a very small candle. We see a few waves, but the deep ocean is full of leviathans and currents we do not yet understand. This is not a failure of science. It is the heart of science. To admit, "I do not know why that happened," is the most honest and powerful statement a researcher can make. The anomalies keep us curious. They prevent us from becoming arrogant. As long as there are impossible things in the sky, there will be a reason to keep looking up, wondering what rules will be broken tonight. When we look up at the night sky, we often feel a sense of peace. We see billions of stars glowing quietly in the vast darkness. We wonder, where is everyone? We have spent decades listening for the radio signals, waiting for a hello, but we have heard nothing. This is the Fermi paradox. For a long time, we thought the silence meant that life is rare. We thought maybe we are special, or perhaps we are the first to arrive. However, there is another possibility, a much darker explanation. This theory does not suggest that the universe is empty. It suggests that the universe is full of life, but everyone is hiding. This is called the dark forest hypothesis, the rules of the game. To understand this theory, we must first look at life through the lens of cosmic sociology. This concept, popularized by the science fiction author Liu Cixin, is built on two very simple, unbreakable rules. Survival is the primary need. Every civilization's first goal is to stay alive. Civilizations grow and expand, but the total matter in the universe remains constant. Think about what this means. Every civilization wants to grow. They need more energy, more planets, and more resources. However, the universe does not get bigger. The pie is only so large. This inevitably creates conflict. In a small village on Earth, if you have a conflict with a neighbor, you can talk to them, you can communicate. But in space, the distances are too vast. It takes hundreds or thousands of years to send a message and get a reply. This creates a chain of suspicion. If you find another civilization, you cannot know if they are good or bad. Even if they are peaceful today, they might become aggressive tomorrow. Even if they claim to be friendly, how can you be sure they aren't lying? And importantly, they are thinking the exact same thing about you. In this environment, trust is impossible. Possible. The hunter in the shadows. This brings us to the central metaphor of the theory. Imagine the universe is a dark forest at night. The forest is not empty. It is full of stealthy hunters. Every hunter is armed. He moves through the trees as quietly as a ghost. He pushes aside branches without making a sound. He tries not to breathe too loudly. He must be quiet because the forest is full of other hunters like him. If he finds another life form, another hunter, an angel or a demon, a delicate infant or a tottering old man, he can only do one thing. He cannot ask questions. He cannot shake hands. To ensure his own survival, he must shoot and eliminate the stranger immediately. In this dark forest, hell is other people. An eternal threat is any life that exposes its own location. The hunter who lights a fire to see better will act as a target for everyone else in the dark. Therefore, the reason we do not hear from aliens is not because they don't exist. It is because they are smart. They know the rules of the forest. They are maintaining radio silence to stay safe. The danger of technology. You might ask, why not just wait and see? Why destroy them immediately? This brings up the concept of a technological explosion. In cosmic terms, time moves very fast. On Earth, we went from riding horses to splitting the atom in less than 200 years. To an advanced alien civilization that is millions of years old, 200 years is like the blink of an eye. If they see a young primitive civilization like humans, they might think we are harmless. But because of the distance by the time their spaceship arrives to say hello, we might have advanced past them. We might have become a threat. Because technology advances exponentially, a weak baby can grow into a dangerous giant overnight. Therefore, the safest move for the superior civilization is to destroy the potential threat before it has a chance to grow. It is cold, calculated logic. Humanity, the child with the torch. If the dark forest theory is true, consider the position of humanity. We are currently like a naive child wandering through this dangerous woods. But we are not walking quietly. We are lighting a massive bonfire and shouting at the top of our lungs, "I am here. Is anyone else out there?" For decades, we have been broadcasting radio and television signals into space. We have sent probes like the Voyager spacecraft carrying maps of Earth that show exactly where our solar system is located. We sent the Arecibo message, a powerful radio signal aimed at a cluster of stars describing our DNA, our population, and our location. We did this out of hope. We assumed that any civilization advanced enough to travel the stars must be wise, kind, and moral. We assumed they would want to help us. The dark forest theory suggests this is a fatal mistake. It suggests that the silence of the universe is not a sign of peace, it is a sign of fear. The older civilizations know to keep their heads down. We are the noisy new kids who haven't learnt the lesson yet. We are shouting into the dark, unaware that the predators are listening. Reflection. The comfort of silence. There is something profoundly chilling about this theory, yet it also holds a strange philosophical beauty. We often speak of the loneliness of the human species. We feel sad that we seem to be the only intelligent life in our solar system. We look at the vast distance between stars and feel small and isolated. We view this isolation as a curse. But if the universe really is a dark forest, then that loneliness is actually our shield. Our isolation is the only thing keeping us alive. The vast distances between stars are not walls that imprison us. They are castle moats that protect us from things we cannot comprehend. This perspective changes how we view the night sky. Instead of looking up and feeling sad that it is so quiet, perhaps we should feel relieved. The tsama is safety. The darkness is a blanket that hides us. There is a certain peace in the idea of hiding. It suggests that maybe we don't need to conquer the galaxy. Maybe we don't need to be heard by everyone. There is dignity in a quiet existence. Just as a person can find peace in a solitary cabin in the woods far away from the noise and conflict of the city, perhaps humanity is meant to live quietly on our pale blue dot. We are safe in our obscurity. We are safe because we are small. It forces us to ask ourselves a difficult question. Is it better to be alone and safe, or connected and in danger? Perhaps the great silence is not a problem to be solved. Perhaps it is the natural state of a mature universe. The young civilizations shout and scream for attention, while the old, wise civilizations rest in the quiet dark, watching, waiting, and surviving. In the end, the dark forest theory teaches us to cherish our quiet little corner of the cosmos. It reminds us that sometimes the unknown is not an adventure waiting to happen, but a danger waiting to be avoided. It suggests that in a universe full of hunters, the greatest luxury of all is simply to be left alone. To understand what 3i Atlas might actually be, we must first look at a concept that has terrified and fascinated sci-fi readers and scientists alike, the dark forest theory. Imagine the universe is not a friendly ocean full of islands, but a dark, dense forest at night. In this forest there are many hunters, civilizations, but they are all hiding. They stay silent because they know that if they reveal their location by shouting, making a fire, or sending radio signals, another hunter might see them as a threat and eliminate them. In this theory, the smartest civilizations are the quietest ones. They do not broadcast, "Hello, we are here," to the stars. Instead, they listen, and occasionally they send out a scout. If we apply this logic to 3i Atlas, its silentness makes perfect sense. For months, astronomers listened for radio waves coming from the object. They heard nothing. A natural rock would be silent, of course, but so would a sophisticated probe from a cautious civilization. If 3i Atlas is a machine, it is likely a passive observer. It is not here to invade, it is here to update a map. It is recording the location of our planets, the chemical makeup of our atmosphere, and perhaps the chaotic radio signals leaking from Earth. The perfect camouflage. If you wanted to send a spy drone into a forest, you wouldn't paint it bright orange. You would disguise it as a bird or a branch. In space, the best disguise is a comet. Comets are the most common travelers in the galaxy. They are everywhere. A probe designed to look like a comet, an icy, dirty snowball, could travel through star systems without raising any alarms. This brings us to the specific behavior of 3i Atlas. Unlike other objects that clearly look artificial, Atlas behaved almost exactly like a comet. It had a tail of gas and dust. It grew brighter as it got close to the sun. However, this could be the ultimate engineering trick. A sufficiently advanced probe might use frozen gases on its outer shell to cool its systems or to steer itself. When these gases heat up and shoot off into space, they create a tail that looks natural to our telescopes, but actually allows the object to make tiny adjustments to its path. It is hiding in plain sight. A tale of two visitors, Atlas versus Oumuamua. We cannot discuss 3i Atlas without comparing it to its older brother Oumuamua, which visited us in 2017. Comparing them is arguably the most important part of this investigation. Oumuamua was the weird one. It was shaped like a long cigar or a flat pancake, which is very rare for a natural space rock. It was tumbling end over end. Most disturbingly, it accelerated as it left the solar system, but it did not have a visible tail of gas to push it. It moved like a ship with an invisible engine. Because it was so strange, it immediately made people scream, "Aliens!" 3i Atlas, on the other hand, was the normal one. It looked rounder. It had a visible tail. It disintegrated, broke apart as it got close to the sun. But here is the statistical problem. Space is incredibly mind-bogglingly big. The chances of our solar system capturing two distinct interstellar objects in less than 5 years are extremely low, if they're just random rocks floating in the void. The fact that we saw two of them in such a short time suggests one of two things. Space is crowded. The galaxy is absolutely full of these drifting rocks, and we are just now getting better at seeing them. They are connected. If Oumuamua was the fast flyby scout meant to take a quick picture, maybe 3i Atlas was the close inspector meant to get near the sun. The fact that Atlas broke apart does not prove it was a rock. If it was a probe that had been travelling for millions of years, its structure might have been old and weak. Or perhaps the self-destruction was intentional, a way to ensure that no technology fell into human hands. The philosophy of the gaze. Now let us move away from the physics and look at the feeling this creates. Let us step back and think about what it means to be observed. For all of human history, we have been the ones looking up. We look at the moon, we look at Mars, we look at the stars. We are the active observers. We name the stars, we chart the galaxies. We feel like the main characters of the universe because we are the only ones watching. The presence of an interstellar visitor, whether it is a rock or a machine, flips this dynamic upside down. Suddenly we are not the watchers, we are the watched. If 3i Atlas was a probe, it means that somewhere light years away there is a record of us. There might be a digital file that contains data about Earth's water, our oxygen levels, and our position in the galaxy. We are no longer hidden in the dark, we have been found. From fear to awe. How does this change how we sleep tonight? The immediate reaction might be fear. The idea of a didn't watcher sounds like a horror movie. We worry about invasion or conflict. But there is a different way to look at it, a perspective of awe. Awe is that feeling you get when you look at the Grand Canyon or a massive thunderstorm. It is a mix of feeling very small and yet very connected to something huge. If we are being watched, it means we are interesting. It means the Earth is rare enough and special enough that a traveller from the stars, either a random rock or a deliberate machine, came to visit. It validates our existence. Tonight, when you lay in bed, the knowledge that an object from another star system passed by us should not cause nightmares. Instead, it should expand your imagination. It means the borders of our reality are not closed. We live in an open system. The wind from other stars blows through our backyard. We are not isolated in a bubble. We are on a small stage in a vast dark theatre. And just maybe for a brief moment, someone in the audience turned their head to look at us. That is not terrifying, it's beautiful. It reminds us that the universe is much grander, much older, and much more mysterious than the daily worries of our human lives. On November 4th, the silence of the deep void was broken not by a sound, but by a stream of invisible numbers. Out there in the cold, dark expanse between the worlds, the spacecraft known as JUICE, the Jupiter Icy Moons Explorer, executed its critical maneuver. To the machine, it was a routine series of commands and binary adjustments, but to the observers back on Earth, it was the pivotal moment they had spent years praying for. The event itself happened in a flash. The probe passed through the target zone, its sensors drinking in the magnetic fields, the spectral fingerprints of the ice, and the faint ghostly whispers of particles trapped in orbit. It was a moment of absolute contact with the unknown. The reality of what is out there was captured frozen in the memory banks of a computer floating millions of kilometers away. However, on Earth, November 4th came and went with no headlines, no breaking news banners, and no sudden revelations. The screens in the control center showed that the event had happened, but they did not show what had happened. The truth had been captured, but it had not yet arrived. This brings us to the frustrating, confusing, and deeply human question that followed. Why do we have to wait until February 26 to see what the machine saw? The delay is not an accident. It is a necessity born of physics and caution. To understand this, we must look at the journey the data must take. The information collected by JUICE is not a simple photograph that can be uploaded to the internet in seconds. It is a dense, heavy, and complex set of raw signals. Sending this data back to Earth is like trying to pour an entire ocean through a drinking straw. The distance is the first enemy. The signal travels at the speed of light, but even light gets tired when it has to cross the solar system. By the time the radio waves reach the large antennas in the desert plains of Earth, they are no louder than a whisper. We cannot stream this data in high definition. We must trickle it down bit by bit over weeks and months. Furthermore, the timeline extends to February 2026 because of the position of the planets. There are periods where the Sun sits directly between the Earth and the probe, drowning out all radio communications in a storm of solar static. During these times, the truth is stuck on the other side of the fire, unable to reach us. We must wait for the celestial mechanics to align for the path to clear so the probe can speak to us again without interruption. But the most significant reason for the delay is not the machine, it is the human element. This is the bureaucracy of truth. Once the raw data arrives, it looks nothing like a discovery. It looks like noise. It is a chaotic mess of static and numbers that makes no sense to the untrained eye. Scientists need time to clean this data. They must calibrate it to it, filtering out the background radiation of the universe and the electronic hum of the spacecraft itself. They must verify that a spike in the graph is actually a water plume and not just a glitch in a sensor. This process, the transformation of raw data into proven fact, is slow, tedious, and essential. Releasing the data too early before it is understood risks spreading falsehoods. Therefore, the date of February 2026 was set not just as a deadline for download, but as a deadline for understanding. This creates a profound philosophical realization about the nature of time in our universe. We live in an age of instant gratification. If we want to know the weather, we tap a screen. If we want to talk to a friend on the other side of the world, we video call them instantly. We have convinced ourselves that now is the only time that matters. But the universe does not operate on human time. The universe operates on deep time. The stars we see in the night sky are a perfect example of this latency. When you look at a star, you're not seeing it as it is now. You are seeing it as it was 10, 100, or 1,000 years ago. The light takes time to travel. We are always looking into the past. The now that we perceive is actually an echo of an event that happened long ago. The situation with JUICE mirrors this cosmic reality. The truth of what happened on November 4th exists. It is real. The interactions between the magnetic fields and the icy crusts have occurred. But for us, the perception of that truth is delayed. There is a gap between the event happening and human awareness of the event. This gap is the latency of truth. In this gap, we find the necessity of patience, a virtue that modern society has largely forgotten. The wait until February 2026 forces us to slow down. It reminds us that the universe is vast and we are small. We cannot rush the orbit of the planets and we cannot rush the speed of light. We are at the mercy of the physical laws that bind existence. There is also a strange beauty in this bureaucratic delay. In the months between the event and the revelation, the data sits in a kind of purgatory. It is a secret held by the hard drives waiting to be born into human knowledge. It reminds us that reality exists independent of us. Even if we never received the data, the ice would still shift and the moons would still spin. The universe does not need us to watch it for it to be real. The delay also highlights the difference between information and wisdom. Information is instantaneous. Wisdom takes time. The raw data is just information. The report that will be released in 2026 is wisdom. It requires the human mind to sit with the numbers, to debate them, to doubt them, and finally to understand them. So as we wait for the calendar pages to turn toward 2026, we are doing more than just waiting for a file download. We are engaging in an ancient practice of looking into the dark and waiting for a signal. We are learning to trust that the truth is coming, even if it arrives slowly. November 4th was the day the universe spoke. February 2026 will be the day we finally learn enough of the language to understand what it said. Until then, we wait in the quiet latency, knowing that the truth is already there, travelling across the void, making its way home to us. The journey of the comet is not merely a straight line through the darkness, it is a complex, elegant performance choreographed by the most powerful force in the universe, gravity. As the comet dives deeper into the heart of the solar system, it begins a phase that scientists call the perihelion. This is the moment of truth, the point in the orbit where the celestial traveller comes closest to the Sun. It is a place of extreme danger, but also of incredible speed. Imagine a roller coaster at the very top of its highest track. As it drops, it gathers speed, moving faster and faster until it reaches the bottom. The comet does exactly this. As it falls toward the Sun, the gravitational pull grabs hold of it, dragging it inward with immense power. During this approach, the comet is no longer just drifting, it is racing. At the exact moment of perihelion, the comet reaches its maximum velocity. It skims the surface of the solar fire, enduring temperatures that could melt steel, all while moving at speeds that are hard for the human mind to comprehend, hundreds of thousands of kilometers per hour. This creates a phenomenon known in physics as the Loeb effect. While the name sounds technical, the concept is actually quite simple to understand. Think of a child on a swing set. If you push the swing when it is at the highest point, it does not add much speed. But if you give a push right at the bottom of the arc when the swing is moving its fastest, the extra energy creates a massive boost. Gravity works in a similar way. By falling deep into the Sun's gravity well, the area where the Sun's pull is strongest and reaching that incredible top speed, the comet gains kinetic energy much more efficiently. It acts like a cosmic slingshot. The Sun whips the comet around, changing its direction and flinging it back out into the deep solar system with renewed energy. If the comet survives this fiery trial, if it does not break apart under the intense heat and tidal forces, it begins its outbound journey. This is when the geometry of the solar system aligns for the observers back on Earth. By December, the comet approaches our planet. This is not a collision course, but a flyby. For us standing in our backyards or looking through telescopes, this is the moment the ghost becomes visible. The approach to Earth in December is a quiet event compared to the violence of the perihelion. It is a silent gliding through the night sky. However, the mechanics behind it are precise. The gravity of Earth tugs at the comet slightly, and the comet tugs back at Earth, though the comet is too small to affect our planet's orbit. It is a delicate meeting. For a few weeks, the geometry of the Sun, the Earth, and the comet creates the perfect angle for sunlight to reflect off the comet's tail, making it glow brightly against the darkness. This is the reward for the astronomers who have calculated the numbers for months. However, the Sun and Earth are not the only players in this dance. Looming in the darkness is the king of planets, Jupiter. The influence of Jupiter cannot be overstated. It is so massive that it acts as a bully in the solar system, pushing and pulling asteroids and comets off their original paths. After the comet passes Earth and heads back out into the cold void, it may eventually encounter Jupiter's gravitational field. A flyby of Jupiter is a chaotic event. Because Jupiter is so heavy, its gravity can completely rewrite the future of a comet. It can speed the comet up, throwing it out of the solar system forever, never to return. Or it can slow the comet down, trapping it in a smaller orbit, turning a long-distance traveller into a permanent resident of the inner solar system. This interaction is a reminder that nothing in space is static. The path is never truly fixed. It is always being negotiated by the heavy giants that live in the dark. When we step back and look at all these events, the diving speed of the perihelion, the slingshot of the Loeb effect of the December visibility, and the gravitational nudges from Jupiter, we are left with a profound realization. This is the clockwork universe. For centuries, humans have looked up at the sky and felt anxious. We worry about comets as omens of doom. We worry about the sun dying. We worry about asteroids hitting us. We project our human fears, our loves, and our short lifespans onto the cosmos. But the universe does not share our anxiety. It operates with the cold, perfect precision of a master clockmaker. The motion of the comet is governed by laws that were true 1 billion years ago and will be true 1 billion years from now. Gravity does not make mistakes, it does not hesitate. The comet does not choose to speed up near the Sun, it simply must. It obeys the curvature of space and time without question. There is a strange comfort in this indifference. The solar system is a giant machine ticking away in total silence. The planets and comets are like gears in this machine. They turn and spin in perfect synchronization not because they are being guided by a conscious hand, but because the laws of physics are absolute. When we watch the comet pass by in December, we are watching the gears of the universe turning. It reminds us that we are part of a system much larger than our daily lives, our politics, or our worries. The dance of gravity is effortless. It is a ballet without a conductor. The comet falls, the Sun pulls, Jupiter nudges, and Earth watches. It happens whether we are there to see it or not. The universe continues its ticking, rhythmic, eternal dance, beautiful in its complexity, and terrifying in its scale, completely unconcerned with the small, fragile creatures watching from the third rock from the Sun. As the calendar turned toward the final days of the month, a collective shift in energy began to ripple through the global astronomical community. For weeks, the object of their fascination had been hidden, lost in the overwhelming glare of the Sun. It had been a period of blind faith where calculations and mathematical models predicted a path, but no eye or camera could verify the truth. Now, however, the geometry of the solar system was finally aligning in their favour. The date was November 27th. In the logbooks of observatories and the digital calendars of researchers, this date was marked not just as a day, but as a threshold. It was the beginning of the opening window. The concept of an observation window is governed by simple yet unforgiving celestial mechanics. When an object gets too close to the Sun from our vantage point on Earth, it enters a zone where the scattered light in our atmosphere makes observation impossible. It is like trying to spot a candle flame held up against a spotlight. For the past duration, the comet had been traversing this invisible region, but as Earth continued its orbit and the object moved along its own trajectory, the angle between the Sun and the target, known as the elongation, was finally widening. On November the 27th, that angle would reach a critical degree, just enough to allow telescopes to peer into the twilight sky before the Sun rose or just after it set and catch a glimpse of the traveller. The preparation for this moment was a synchronized dance spanning continents. It began in the east, where the shadow of night falls first. In the high deserts of Australia and the mountaintops of Japan, dome shutters slid open with a low mechanical rumble. These were not casual observations. Every instrument had to be calibrated to perfection. Technicians spent hours checking the cooling systems of the cameras, ensuring the sensors were chilled to nearly -100 degrees Celsius to minimize electronic noise. In the thin, cold air of high-altitude observatories, the silence was heavy, broken only by the hum of servers and the occasional click of a keyboard. Across the Pacific, on the summit of Mauna Kea in Hawaii, the anticipation was even more palpable. Here above the cloud layer, some of the largest eyes on Earth were waking up. The operators were not just looking for a fuzzy dot, they were hunting for details. They needed to know if the nucleus was intact. They needed to analyze the spectrum of light reflecting off the tail to see what gases were being released. The preparation involved a rigorous checklist. Mirrors were adjusted by fractions of a millimeter. Adaptive optics systems, which use lasers to correct for the blurring effect of the atmosphere, were powered up and tested. The goal was to be ready the exact second the sky was dark enough to see, but the object was still high enough above the horizon to be captured. This period of waiting created a unique psychological atmosphere, a blend of professional discipline and raw human suspense. Astronomy is often viewed as a cold science of numbers and physics, but in moments like this it becomes deeply emotional. There is a quiet anxiety that settles over a control room as the countdown begins. The scientists knew that comets are fragile things. They are essentially dirty snowballs held together by weak gravity. The close passage by the Sun, the very event that makes them bright and beautiful, is also the event that can destroy them. The intense heat and gravitational tidal forces could have ripped the object apart while it was hidden in the glare. Therefore, the opening of the window was not just about data collection, it was about confirmation of survival. As the astronomers sat in their ergonomic chairs sipping lukewarm coffee and watching the telemetry screens, they were plagued by the question, is it still there? Or will we point our billion-dollar instruments at the coordinates and find nothing but a fading cloud of dust? This mix of hope and fear is the heartbeat of exploration. It is the feeling of a diver waiting to see if a pearl is inside the oyster, or a sailor waiting for land to appear through the fog. The atmosphere in these control rooms is distinct. It is a dark environment usually lit only by the red glow of monitors to preserve night vision. Voices are kept low, almost distinctively reverent. When the window opens, time seems to compress. They might only have 20 or 30 minutes of good viewing time before the rotation of the Earth hides the object or the rising sun washes out the image. Every second counts. There is no room for error, no time to reboot a frozen computer or fix a stuck filter wheel. The tension is static electric and shared across the globe via instant messaging channels and secure data networks. A team in Chile might message a team in the Canary Islands, comparing weather reports and sharing target coordinates, creating a continuous relay of vigilance. As the critical hour approached on the morning of the 27th, the world was effectively turning its face toward the dawn. In the northern hemisphere, where the viewing conditions were expected to be most favourable, the pre-dawn sky began to lighten. This is the nautical twilight, a time when the horizon becomes visible, but the stars are still sharp. For the astronomers, this is the golden hour. They watched the weather monitors with intensity. Humidity, wind speed, and cloud cover were the enemies. A single patch of clouds drifting over the mountain at the wrong moment could ruin weeks of planning. But on this specific day, for many, the skies held clear. The large telescopes slewed into position. The movement of these massive structures is surprisingly graceful, a silent glide of tons of steel and glass. They pointed toward the eastern horizon, low down, piercing through the thickest part of the Earth's atmosphere. The tracking motors engaged, counteracting the rotation of the planet to keep the field of view locked steady. The feeling in those final moments is difficult to describe. It is a suspension of breath. It is the culmination of the theoretical meeting the physical. For weeks, the object had existed only as a set of orbital elements, a line of code in a simulation. How photons, particles of light that had travelled millions of kilometres, bounced off the icy surface of the comet and travelled millions of kilometres back, were about to strike the silicon detectors of the cameras. The opening window was not a metaphor, it was a physical reality, a gap in the blinding curtain of the sun through which humanity could finally see. As the first exposures were taken, the screens remained blank for a few seconds, the computers processing the raw data. The spinning icon of a loading bar became the centre of the universe for the observers. In that brief pause, the silence in the observatories was absolute. It was a shared moment of vulnerability. They were looking into the unknown, hoping to find a visitor from the distant edges of the solar system that had survived its trial by fire. The window was open, the world was watching, and in the quiet hum of the machines, the human spirit of curiosity reached out once again into the vast waiting dark. We have arrived at the end of our long journey together. It feels appropriate that we end here in the quiet just as the lights go down. Imagine for a moment that you are sitting in a grand theatre. The show is over, the applause has faded, and the heavy dark red fabric of the stage curtain has lowered. We call this the velvet curtain. In the world of theatre, the curtain hides the backstage machinery, the ropes and the lights. But in our journey, the velvet curtain is the night sky itself. It is that beautiful dark blanket that wraps around our little planet every single evening. Throughout this series, we have tried to peek behind that curtain. We have travelled very far in our minds. We started with the ground beneath our feet, looking at the dirt and the roots. We zoomed in closer than our eyes could ever see, looking at the tiny atoms that build everything. We learned that these atoms are mostly empty space dancing with energy. We realised that the solid chair you are sitting on or the bed you are lying in is actually a buzzing field of tiny particles vibrating and holding together to support you. Then we travelled outward. We left the Earth behind. We floated past the moon, silent and grey. We drifted past the burning sun, which gives us all our warmth. We moved out past the giant planets of our solar system and into the deep cold waters of interstellar space. We talked about light and how it takes time to travel. We learned that when you look at a star, you are looking into the past. You are seeing history written in light. We realised that the universe is not just a place we live in, it is a story that is still being told. Now we bring all those pieces back together. It might feel overwhelming to think about how big everything is. When we talk about billions of years or trillions of miles, the human brain can feel a little dizzy. It is natural to feel small, but this is where we change our perspective. This is the moment of quiet awakening. To be awake to the universe does not mean you need to be afraid. Sometimes when people realise how tiny Earth is compared to the rest of the vast galaxy, they feel a sense of panic. They feel like they do not matter. But I want you to feel the exact opposite tonight. I want you to feel an immense sense of relief. Think about it this way. If the universe is infinite, and if there are more stars than there are grains of sand on every beach on Earth, then your problems, your worries and your stress are also very small. The universe is not asking you to carry the weight of the world on your shoulders. The universe carries you. Gravity holds you down gently. The atmosphere gives you air to breathe without you even asking for it. The sun rises every morning to warm your skin. You're being taken care of by the laws of nature. There is a beautiful freedom in accepting that we do not know everything. We humans love to have answers. We want to know why we are here, where we are going, and what it all means. But behind the velvet curtain there is a lot of mystery, and tonight we are going to accept that mystery. We are going to make friends with the unknown. You do not need to know how the engine of the car works to enjoy the ride. You do not need to understand the complex fusion of hydrogen and helium in the sun to enjoy a sunny day. And you do not need to solve the puzzle of existence to have a good night of sleep. Let the mystery be a soft pillow for your mind. It is okay not to know. It is okay to just be. As you lie there, close your eyes if you haven't already. Feel the weight of your body sinking into the mattress. Imagine that the velvet curtain of the night is wrapping around you not to trap you but to keep you safe and warm. You are hidden away from the noise of the day. Reflect on the fact that the atoms in your body, the calcium in your fingernails, the iron in your blood, the carbon in your skin were all cooked inside giant stars that exploded billions of years ago. You are quite literally made of stardust. You belong to this universe just as much as a star belongs in the sky or a wave belongs in the ocean. You're not a stranger here. You're a child of the cosmos. There is a special kind of silence behind the curtain. It is the silence of deep space, but it is not empty. It is a peaceful silence. Let that silence fill your room now. Let it quiet the thoughts racing in your mind. Imagine those thoughts are just little clouds drifting across a dark sky. Watch them float by, but do not try to catch them. Let them go. We are small, yes. If you look at the Earth from the edge of the solar system, it looks like a pale blue dot, just a speck of dust suspended in a sunbeam. But think about what happens on that speck. We love, we dream, we create music, we comfort each other, we sleep. Being small does not mean we are insignificant. It makes us rare. In all the cold vastness of space that we have explored, this little blue planet is the only place we know of where there is warmth, laughter, and soft blankets. You are in the safest place you could possibly be. So as we lower the curtain on this journey, let your breathing become slow and steady. Inhale the stardust. Exhale the worry, inhale the peace of the galaxy, exhale the tension of the day. You have travelled far. You have looked into the abyss and found that it is not scary, it's just vast and waiting. You have learned that you are connected to everything from the dirt on the ground to the light of the distant nebula. You are part of a grand, beautiful and mysterious design. Now it is time to rest. The stars will keep burning while you sleep. The planets will keep turning in their perfect circles. Gravity will keep holding you safe. You do not need to do anything else. The show is over. The audience has gone home. The lights are out. It is just you and the gentle dark velvet of the night. Let go of the need to understand. Let go of the need to control. Just drift. Float in the great ocean of the cosmos. You are home. You are safe. You are loved by the universe that made you. Good night, traveller. Sleep well among the stars.